Welcome to DAR Tutors. Today, we will explore the concepts of nonlinear regression, a powerful tool in mathematics and statistics. In this video, you will achieve several key learning objectives. First, you will be able to distinguish between linear and nonlinear regression models and identify situations where nonlinear regression is necessary. Second, you will understand the fundamental principle of nonlinear regression, the minimization of the sum of squared residuals, or SSREs. You'll see how this principle is applied to nonlinear functions. Third, you will learn how to linearize certain nonlinear models using logarithmic transformations. This will allow you to apply the familiar methods of linear regression to solve nonlinear problems. Finally, you will become proficient in using technology, such as graphics calculators, to perform complex nonlinear regression analyses and interpret the results. Let's begin by defining nonlinear regression. In simple linear regression, we seek a straight line that best fits a set of data points. The model is a linear function of its parameters. In some cases, our data does not follow a linear trend. It might be quadratic, exponential, or power law. Nonlinear regression is the process of fitting a nonlinear function to a set of data points. The goal is the same as in linear regression: to find the function that best describes the relationship between the variables. The core problem is to determine the values of the coefficients in our nonlinear model that provide the best fit. This involves minimizing a measure of the difference between the actual data and the predicted values from our model. The principle of best fit is based on residuals. A residual is the vertical distance between an observed data point and the point predicted by our model. We calculate this distance as the observed value y minus the predicted value y. So, the residual for the ith point is given by d equals y minus y hati. To find the best fit model, we need to minimize these errors. The standard approach is the principle of least squares. Because some residuals are positive and some are negative, we square them before adding them up. This gives us the sum of squared residuals, or SSRs. The formula for the sum of squared residuals is the sum of the square of each residual, from I equals 1 to n. Our goal is to find the parameters of the model, like the a and b and c in a quadratic equation, that make this sum of squared residuals as small as possible. This minimization is how we determine the line or curve of best fit. Let's apply the concept of SRS to a nonlinear model. Consider a simple exponential model. Suppose we want to fit the model y equals a times b to the power of x to some data. For each data point, the model predicts a value y by plugging xi into our model equation. So the predicted value is y hati equals a times b to the power of xi. The residual for this point is the difference between the observed y and the predicted y. The residual is d equals y minus a times b to the power of xi. To find the best fit exponential curve, we would need to find the values of a and b that minimize the sum of the square of these residuals. This is a nonlinear optimization problem that we typically solve with technology. While nonlinear regression is powerful, for some models, there's a more straightforward technique: variable transformation. This allows us to convert a nonlinear relationship into a linear one. The process involves applying a mathematical function, such as a logarithm or a reciprocal, to one or both of our variables. The goal is to produce a new set of variables, which we can call x and y, that have a linear relationship. Once we have this linear relationship, we can use standard linear regression to find the equation of the line of best fit for our transformed data. From this linear equation, we can then work backward to find the parameters of our original nonlinear model. This technique is extremely useful for exponential and power law models. Let's demonstrate this with an exponential model. Suppose our data follows the relationship y equals a times b to the power of x. To linearize this, we take the natural logarithm of both sides of the equation. Taking the log gives us the natural log of y equals the natural log of a times b to the power of x. Using the logarithm property that the log of a product is the sum of the logs, we can rewrite the right side. This becomes the natural log of y equals the natural log of a plus the natural log of b to the power of x. Now we use another logarithm property, which allows us to bring the exponent x down as a multiplier. This results in the natural log of y equals ln a plus x times ln b. Let's rearrange this to resemble a linear equation. We can write it as the natural log of y equals the natural log of b times x plus the natural log of a. If we define a new variable capital Y as ln y, a new variable capital X as x, the slope m as ln b, and the y-intercept c as ln a, we get a perfect linear relationship. Y equals mx plus c. This means if we plot len my y against x, we should get a straight line. From the slope and intercept of this linear model, we can then find our original parameters, a and b. The value a is simply e to the power of the y-intercept, c. The value b is e to the power of the slope, m. We can use the same technique for a power law model. Consider the model v equals a times x to the power of n. Here, both the base variable x and the coefficient a are multiplied. To linearize this, we again take the natural logarithm of both sides. This gives us e n y equals e n axn. Using the logarithm property for products and powers, we can expand the right side. The result is ln y equals ln a plus n times ln x. Let's rearrange this. This becomes ln y equals n times ln x plus ln a. If we let capital Y equal ln y, capital X equal ln x, the slope m equal n, and the y-intercept c equal ln a, we find another linear relationship. This means if we plot ln against ln x, the points should form a straight line. After performing linear regression on the transformed data, we can find our original parameters. The exponent n is simply the slope of the line, and the coefficient a is e to the power of the y-intercept. Let's work through an example of this transformation in practice. A cinema records audience attendance, A, over a period of D days after a movie's release. We want to find the relationship between attendance and the number of days. We start by drawing scatter diagrams of A against D, and then transformed variables like ln A against D, A against ln D, and so on. Let's draw a diagram of ln A versus D. By plotting the transformed data, we observe that the points align very closely to a straight line. The linear appearance of this scatter diagram strongly suggests that an exponential model of the form A equals a times B to the power of D is appropriate. Using our graphics calculator, we perform linear regression on the variables D and ln A. Let's say we find the linear equation to be approximately ln A equals or 61 d plus 4.02. Now we need to convert this back to our original variables. Recall that ln A equals d ln B plus ln A. By comparing the two equations, we can see that the slope, 0.0461, corresponds to ln B, and the y-intercept, 4.02, corresponds to ln A. To find A and B, we calculate e to the power of these values. A is e to the power of 4.02, which is about 55.7. B is e to the power of 0.461, which is about 0.95. This gives us our final exponential model. A equals 55.7 times 0.955 to the power of D. This model describes the attendance decay for the film. This transformation allowed us to use simple linear regression to fit a complex exponential curve. Now, let's address the question of how to handle models that cannot be easily linearized. This brings us back to nonlinear regression using technology. The IB Mathematics AI/HL curriculum often focuses on fitting quadratic, cubic, and quartic models using a graphics calculator. For example, to fit a quadratic model y equals x squared plus bx plus c, your calculator performs a linear regression, but on transformed variables. It treats x squared, x, and a constant as separate variables, and finds the linear relationship between them. The calculator's algorithm minimizes the sum of squared residuals for you, providing the values for a, b, and c that result in the best fit curve. This process is very similar for cubic and quartic models, where the calculator simply includes higher powers of x in its calculations. For a cubic model, it considers x cubed, x squared, x, and the constant. For a quartic, it includes x to the power of 4. The underlying calculation for the calculator is still a type of linear regression, but it achieves the goal of fitting a nonlinear curve. A key measure of how well a model fits the data is the coefficient of determination, r squared. The value of r squared tells us the proportion of the variation in the dependent variable that can be explained by our regression model. It is calculated by dividing the explained sum of squares, SSS/EXP, by the total sum of squares, SS/D/E2T. A higher r-squared value, closer to 1, indicates a better fit, meaning our model does a good job of explaining the data's variability. This metric is very useful when comparing different models for the same dataset. The model with the highest r-squared is generally the preferred choice. A common question is, does adding more terms to a polynomial model always give a better fit? For example, if you fit a linear model, then a quadratic, then a cubic to the same data, which will have the lowest sum of squared residuals? The answer is, a cubic model will always have an SSRE as less than or equal to a quadratic model. Similarly, a quadratic model will always have an SSRE as less than or equal to a linear model. This means that as you increase the degree of the polynomial, you will always get a model that fits the observed data at least as well, if not better. The reason for this is that a lower degree polynomial is a special case of a higher degree one. For instance, a quadratic model y equals x squared plus bx plus c is a cubic model where the coefficient of x cubed is 0. The optimization algorithm can choose to set that coefficient to 0 if that gives the best fit. However, a better fit to the data does not always mean a better model. This is where we must be careful. A complex model that fits the data perfectly might be overfitting the data. This means it captures not just the underlying trend, but also the random noise in the data points. An overfit model is often a poor predictor for new data. The goal is to find the simplest model that provides a reasonable and accurate fit. We achieve this by balancing the desire for a low SREs with the principle of parsimony or simplicity. We've covered several key ideas. Let's briefly recap. First, nonlinear regression fits curved models to data, and its goal is to find the function that best describes the relationship. Second, the principle of least squares guides this process, aiming to minimize the sum of squared residuals, SSREs, which is the sum of the squared vertical distances between observed and predicted values. Third, for exponential and power models, we can use variable transformations, particularly logarithms, to linearize the data. This allows us to use standard linear regression techniques. Finally, for polynomial models like quadratic or cubic, we use technology, such as a graphics calculator, which performs a specialized linear regression to find the best fit curve. We also saw the importance of balancing model complexity with fit, avoiding overfitting, and using the coefficient of determination, r squared, to assess model quality. This concludes our review of nonlinear regression for the IB/AI/HL curriculum. We encourage you to practice these concepts with additional problems. If you require further expert tuition in the IB, A-Level, or IGCSE curricula, please contact DAR Tutors. Our specialist teachers can provide personalized support and guidance to help you achieve your academic goals. Now, let's test your understanding with some IB-style practice questions. A fully worked solution will follow each question. Here's our first question. You can pause the video to work on it yourself. Here's the solution to question 1. First, we justify our model choice. We draw scatter diagrams for V against T and for transformed variables. The graph of V versus T appears to be a straight line. This indicates an exponential relationship of the form y equals a times b to the power of t. We use linear regression on t and ln v. Let's perform the calculation. The linear regression for t ln v gives the equation ln v equals 222t plus 2.76. This is of the form ln v equals ln bt plus ln a. From this, we find a equals e to the power of 2.76, which is approximately 15.8, and b equals e to the power of 0.122, which is approximately 0.801. So our final model is v equals 15.8 times 0.801 to the power of t. For part B, we need to estimate the water remaining after 5 hours. We substitute t equals 5 into our model. V equals 15.8 times 0.801 to the power of 5, which gives approximately 5.16 liters. Here is our second practice question. Again, pause the video to solve it. Here is the solution to question 2. We justify our model choice. Newton's law of gravitation suggests a power law relationship. F is proportional to 1 over d squared, which can be written as F equals k times d to the power of 2. To check this, we plot ln F against ln d. The graph shows a very strong linear trend, confirming a power law model is appropriate. We perform linear regression on the transformed data ln d and ln f. Let's assume our calculator gives the linear equation ln f is 2000 ln d plus 9.542. The slope, 2000, is our power n. The y-intercept, 9.542, is ln a. So a is e to the power of 9.542, which is about 13936. Our model is f equals 13936 times d to the power of 2, or f equals 13936 divided by d squared. This fits Newton's law very well, with the exponent being almost exactly 2. For part B, we substitute d equals 20 centimeters into our model. F equals 13936 divided by 20 squared, which gives 34.84 newtons. Note that our predicted value of n was 2000, so this model is an excellent input as an excellent fit. Here is our third practice question. Here is the solution to question 3. For part A, we calculate the natural logarithm of t for each time point and plot ln t against t. The resulting scatter diagram shows a clear linear trend. This confirms that an exponential model of the form t equals a times b to the power of t is appropriate for describing the cooling process. To find this model, we perform linear regression on t and ln t. Our calculator might give the linear equation ln t equals 222 plus 4.02. For part B, we need to estimate the temperature at the start of the experiment, which corresponds to t equals 0. We can simply substitute t equals 0 into our model. T equals a times b to the power of 0, which simplifies to just a. Since ln a equals 4.02, a equals e to the power of 4.02, which is approximately 55.7 degrees Celsius. Therefore, the estimated initial temperature of the coffee was 55.7 degrees Celsius above room temperature. Let's tackle our fourth practice question. Here is the solution to question 4. For part A, we input the data into a graphics calculator and use the quadratic regression function. The calculator will output the coefficients a, b, and c. The regression will yield an equation approximately t equals 0.995 times n squared, plus 1.15 times n, plus 10.6. This is our best fit quadratic model. For part B, we predict the time to sort 10,000 items and discuss reliability. We substitute n equals 10,000 into our model. This gives us t equals 0.995 times 10,000 squared, plus 1.15 times 10 plus 10.6. Calculating this gives a time of approximately 1,000 and 6,511 microseconds. Now, about the reliability. Our prediction is for n equals 10,000. However, the data points we use to build the model only go up to n equals 1,000. Making a prediction outside the range of our observed data is called extrapolation. Extrapolation is inherently less reliable than interpolation, which is making a prediction within the data range. Therefore, our prediction of over 1 million microseconds is unlikely to be accurate, as we have no data to confirm the model's validity for such a large value of n. We are assuming the quadratic relationship continues indefinitely, which might not be true for a real-world algorithm. Finally, let's look at our fifth and final practice question. Here is the solution to question 5. For part A, let's explain why a logarithmic model is suitable. If we look at the data, we can see that as the pressure P increases, the pH value B decreases. but it does so at a slower and slower rate. The curve flattens out. This is a classic characteristic of a logarithmic relationship. A scatter diagram of the untransformed data would also clearly show this curve. To find the model, we can use a logarithmic transformation. Our model is of the form b equals a plus ln p. This is already linear in terms of ln p. If we let our new variable capital X be ln p, our equation becomes b equals kx plus a. This is a linear equation where the slope is k and the y-intercept is a. So we calculate ln p for each data point and perform linear regression on the new data, ln p and b. The calculator would give us the equation b e 320 ln p plus 8.78. This means our final logarithmic model is b equals plus 0.320 times ln p plus 8.78. This model can be used to describe the relationship between blood pH and the partial pressure of carbon dioxide. That brings us to the end of our session on nonlinear regression. We've covered the core principles, seen how to use transformations and technology, and worked through several examples. Thank you for joining DAR Tutors. If you found this video helpful and wish to deepen your understanding, or need support in any other IB, A-Level, or IGCSE subject, please don't hesitate to reach out to us for expert tuition. Good luck with your studies.